Hello, everyone. Hopefully, you still have some energy to listen to me. Um, let's see how we. So that's me. So I am going to talk about BCI today, but I have to say that we are not really a BCI kind of company, and we are not really concentrating on this as our main topic. I'll mention later what it is that we are doing. But before getting into this, let me cool you down a little bit because there was a lot of excitement lately, and I'm afraid some of it is not so justified. So let's talk about what it is that is really one can expect. Okay, so people are talking about BCI as if tomorrow we are going to have an amazing BCI, and this doesn't work? No, doesn't work. Used to work, I guess. Batteries are dead or something. We'll try with this. So maybe one of the worst talks that confused people dramatically was by this former DARPA person who was at Facebook and kind of confused completely between deep brain electrodes and and electrodes that are outside on the forehead or on the skull, and was talking about reaching something like 100 words per minute typing with a BCI. I think we are quite far from that. After saying something so negative, let me talk with you about one project that is actually mind-blowing. It will take about 5 years to really know if this specific project is crazy or actually going to be achieving what it is. It also came from a person who left Facebook, but this specific person, Mary Lou Jepson, is a real expert in optics, and she's building from near-infrared spectroscopy with very detailed optics and actually cameras that exist on every phone today. She's trying to basically build something like a functional MRI that can be put on the head of a person. So like a portable functional MRI, of course, for a fraction of the cost. The only problem is that the technical difficulties there are immense, and time will tell if she can solve them. But this is really the only project that I've seen that can take us to somewhere totally different from where we are. So let's stay where we are. And unfortunately, where we are is quite depressing. Because when you look at people, for example, the locked-in patients that are trying to do a brain-computer interface, then we are talking about a word within 3 minutes or something extremely slow like that. The top person in that is Niels Birnbaumer. This is his latest paper on that topic. And what we tried to do was to kind of demonstrate that one can do this with fewer electrodes. Okay, so that's the topic that we were trying to do. What he's doing is putting multi-electrodes on the skull, asking people to imagine different things, and reading from motor neurons or from neurons that are very close to the skull. This is reasonable because that's kind of the easiest thing to do, and most BCIs work like this. Even the kind of emotive devices using this kind of neurons. If we are trying to do something like this with ALS patients, it's of course more difficult because the cortical neurons, especially the motor neurons, are not functioning, so one cannot do that anymore. And one needs to look for other neurons to read from. If we are looking at functional MRI, we see this amazing work by Adrian Owen and Stephen Laris, And this really brings us to what we are more interested and unfortunately or fortunately, I don't even know how to say it, but most of the patients that I'm dealing with are in much, much worse shape than Shai Rishoni. Shai Rishoni has a functioning brain and functioning eyes at this moment. We are dealing with comatose patients. In that case, it's not clear what exactly is functioning there. And Professor Stephen Laris, who we started to collaborate with quite intensively in the last year, is pretty much the leader in the world in dealing with these patients. And my goal is to remove the functional MRI, PET, CT, and 256 electrodes from his lab and to replace it with 3 electrode sensor. That's really what we are doing. So what they were demonstrating there is that a patient who was considered to be MCH, which is minimal consciousness, which is not clear between locked in to totally vegetative, so it's somewhere on that spectrum, could actually envision herself either playing tennis or walking at home or things like this, and in that respect was able to demonstrate that she could understand what was said to her and could actually envision what was asked from her to do. But of course, doing it with a functional MRI is totally crazy. We are trying to do it with EEG. So this is what we bring. We bring this little 3 electrode on the forehead. Thank you. With a lot of mathematics to really analyze the brain. And what we are trying to be is a neurological bedside monitor. As you know, we have a cardiac monitor, diabetes or glucose monitor, heart rate, whatnot, but nothing really for the brain in the neurology department. And because it is very small, of course, it can go with patients everywhere and then also fit into healthy patients, for example, under VR goggles. But we are really going for the more serious medical applications first. We believe that our first product is actually going to be detection of epilepsy, in fact, pre-ictal activity, which is extremely difficult to detect, and also for migraine. So kind of in a totally different field, but we'll continue. So I want to demonstrate one movie here, this specific one, which shows what we can see in terms of increase of cognitive load, and look at the meter that is going to be on the left, and you will see that it is going up for a very, very short time. Whoops. I think we can do it.
מקסימום ריכוז. בואו
Okay,
נראה.
so that was on
כמה
TV.
כפול כמה זה 400.
Okay,
לא מי יודע מה
so look at the,
במתמטיקה.
it goes up, you saw the meter goes up for a very, very short time, exactly when we're solving that problem.
אוקיי, בואו נראה מה
It's
עוד
going to
יש לנו
happen
פה.
one more
כמה
time.
ועוד כמה בפלוס זה 400. זה כבר מורכב.
Again,
בואו
went
נראה
up for a short time,
320
2
נגיד.
seconds, 3 seconds.
כן, ועוד 80.
Once he found the 2 numbers that actually provide the answer. Maybe this looks trivial to you, but actually it's not. It's far from being trivial. So when you try to measure, say, a few frequencies, alpha or theta, etc., you don't get such accuracy in time for the increase in concentration or cognitive load. This is something that we are relying on for various different tasks, among them for the interface. So let's continue with the interface. As I mentioned, the motivation to deal with minimal consciousness patients is actually coming from the fact that some of them actually wake up. So try to imagine a person who is locked in, but nobody knows that he is locked in. This is like the worst jail that one can possibly think of. This specific person at the age of 12 got into coma About a year later, he got out of coma, and it took another 11 years until people realized that he got out of coma. So for 11 years, he was actually hearing everything that was happening around, hearing his mother saying that she wished he was dead, and only after that kind of woke up and started talking, so he's giving TED Talks about his situation. We are trying to address people like this. So our full system has this little hardware that you see on the left, has the sensor on the forehead. We are using earphones to stimulate the patients, so we kind of stimulate them for a long time, and then we can read their instructions. And the main novelty is this high-level biomarkers that we are creating with a combination of advanced mathematics and machine learning on top of them. So we want to remove the need of reading this electrocardiograph charts to try and really interpret what's going on in the brain. For mathematics, maybe one should look again at what people are using. So in EEG, still the most used method for analyzing EEG was developed not 20 years ago, not 50 years ago, but 250 years ago, okay? So the Fourier analysis or the spectral analysis is what still is being used. In the 1970s, the first kind of time frequency analysis was developed, the wavelets, which mathematicians realized that Fourier is not enough. 20 years later, wavelet packet analysis has been developed. This is a leapfrog improvement on top of wavelets, but somehow not enough people are using it. I was fortunate enough to work with Ronald Koopman, who started it and actually even modified it a little bit a few years later. This is the first time that data-dependent signal processing is really being used. So if you are all excited, I mentioned here deep learning or neural networks, which Jeff Hinton started in the early 80s. So these are data-dependent basic models from data, and as we know, they're doing amazing things nowadays. But when you are trying to do signal processing, you really need to add another layer of data dependent. And we believe that this method for harmonic kind of data, and fortunately a lot of the signal processing is done on harmonic kind of data, this is the perfect match. And so we are combining here harmonic data analysis that is data dependent, of course, with AI in order to do what we are doing. So maybe you've seen this picture before. I guess I cannot use the pointer. So there are several regions here. There's the A region, which is the cognitive region. There's the D region, which is the stress. There's the B, which is the emotional. And the C, one of the most important ones, and the one that is actually not functioning at all with comatose patients, the executive region. We know today that this is medial prefrontal cortex of the brain. A very important region, and this is what we are analyzing. In the last year, we have concentrated on the cognitive region, and we're able to take from there some stripes that have to do with frontal lobe dementia, with various types of dementia and cognitive dysfunctions. So really each line here, which is a decomposition of 120 such components from a single EEG channel, which is the difference between two electrodes, is very important. All right, I'm going to show briefly a project that we did with Prize for Life with Amir Zevin and Daniel Gurfinkel on BCI. So thank you, Shai, for the inspiration, amazing inspiration in everything that we do when trying to read the brain. And of course, your amazing sense of humor and motivation. All right. This is one of the students. So here's what we did. Okay, in accordance to what Adrian Owen and Stephen Laris did. We asked people to imagine several different tasks. So first of all, some kind of breathing. This is what we saw in the movie before. We'll see it again soon. Then we could ask them to imagine that they're listening to music or playing music, performing some kind of physical task, walking, maybe running, some tasks that have to do with long-term memory, short-term memory. Then we read their brain with our device, put it into a simple clustering algorithm, and then it turned out that we were able to detect quite a bit of accuracy of different letters. So basically here we are building an interface with 4 letters. Okay, the movie I'm going to show with Shai is an interface with just 2 letters. One has to be more patient, and I haven't yet found the patience with Shai to work on a 4-letter alphabet. By the way, we are analyzing, for those of you who are interested, we are analyzing the brain with an alphabet of 80 letters. So our brains are, according to what we analyze, are producing kind of a language with an alphabet of 80 letters, but let's not get into this now. So this is really what I want to show from Shai.
Slowly.
Yeah, good. So this is that representation that I mentioned, and Shai is getting a feedback from his representation. So he's performing the task, looking at this, and we are operating this Bluetooth. As you can see, the band is on the forehead, so reading really the frontal lobe and the medial prefrontal and the deep emotional regions. And using this, Shai could learn this task within, I don't know, about half an hour. But of course, if we want to do something else, again, as was mentioned before, more training is needed. For those of you interested, there's a peloton tomorrow at Jerusalem, at Alin. We shall be there. If anyone wants to join us, you're invited. I'm going to stop here and thank you all.